Hi, in this video we'll talk about a concept of a limit. What is it? How do we compute it? And what does it mean in terms of applications in real life, business, and so on? So what is a limit? A short kind of answer is what value does the function approach as x approaches a certain value? And now we're going to talk about the direction. How do you approach it from left and right? What does that mean? And here is the little notation that we use. Limit, LIM, shorthand for limit. And notice how there is a little x approaches some value right underneath. Looks kind of small. That's exactly how we write it. And it's usually attached to a function. But what does it mean? Well, typically if we have any quantity, whether it's sales, whether it's profit, revenue, anything you have equation for, we can figure out, well, what's happening to that quantity either over time, we can observe it, like in this situation, what happens in the long run? Well, as x goes to infinity, could be number of items, could be time, like t, as time goes on, so it could be x or t down here. But what's happening to the sales? So what happens if we sell as many products as we can? Well, hopefully our sales go up. So then this one may be kind of obvious. But you can approach any value, including infinity. So how do we compute this? We're going to take a look at it. But the first thing that I'd like you guys to realize is how do we, let me put this on a pencil. How do we approach a value, okay, in order to understand the limit? So we can do this in a couple of ways. So here is, let's say, a value a. Okay, so we can, let's say if your a is 1, let's say it's 1. Okay, so we can do it both from the left. Let's say if it's from the left, we're literally taking values very close, but a little bit smaller than 1. Let's say 0.9, let's say 0.99, and as close as we can. So you'll see a pattern. Or we can do it from the other side. We can do it with, let's say, 1.1, maybe 1.01. So you'll see how it's getting a little bit smaller, but still closer to the value of 1. So you can either approach it from the left. So notice how there's a little minus sign, sort of like from the negative side. And or we can approach it from the right. So you'll see like a little plus sign, like from the plus side. All right, so very intuitive in a way. So don't let the notation confuse you. So the limit, the two-sided limit, if you don't see the little minus or a plus, means it's a two-sided limit. By definition, basically, the limit exists and is actually equal to all three of these if both sides match. If the left approaches the same value as the right, they both match, then you have a limit, and it's actually the same value as all three of them. And it works both ways, if and only if. If they both match, you have a limit, and vice versa. If you have a limit, the both sides would match. So it kind of works both ways. All right. If they do not match, likewise, the limit does not exist. So it works in the other direction also. Now here is a quick example. So here by a, I actually meant 0. All right, so what if we have a limit as x approaches 0? So again, we can do it from both sides. What if we're doing it from the left? So notice how this function has two pieces. It's called the piecewise function. And we're going to see quite a few of them in the next couple of sections. Let's say if it's this one. Basically, you can take your pencil or finger or maybe eyeball it and basically trace the function as we get closer. And you'll notice, doesn't matter if there's a hole here. It doesn't matter what the actual function is doing, because the limit is sort of like a horizon point. You're trying to get close to it, but you never actually touch it, or you never actually reach it. You know, very rarely that you will. So it's like, what is the value that you're coming close to, but not actually getting there? So you're literally, see how this arrow, you're kind of tracing it and you're coming across. It's the same value. It's -1. Doesn't matter what, if there's a hole there, it's still -1 is the value that it's approaching. And you'll see it in a little bit more exact way shortly. Now, what about from the right? Now, likewise, we're going to come from the right, but notice it's a very different value. Now it's 2. And notice they do not match. There is a little break there. And so the actual limit does not exist. Or D and E for short. Again, mathematicians like sort of kind of a text speak. They like shorthand notation, okay? It's a little bit shorter, but stands for does not exist. All right. So the limit determines what y value, again, is being approached. Now, you may have a whole value. The actual y value of a function may not even exist at that point, and that's okay. They're not always going to be the same, the limit and the y value, the actual y value at that point. So this is something for your, keep in mind for your discussion this week. Let's take a look at this example, all right? What if we have this graph? I already have these arrows from before, but let me erase them real quick so they're not confusing you. All right, so here's the arrows, so let me erase them if I can. All right, now let's take a look. So if we're trying to figure out what limit as x approaches 0 is equal to, all right, now let's just try to think about this. How do we do this? Again, take your pencil or your finger or whatever. So first you're approaching it from the left. That was the little arrow from before. So you're going slowly or maybe fast. Again, there's a hole there, but it's okay. We're approaching some value, okay? Now you're doing the same thing from the right. You're kind of tracing a function. And again, you're getting closer to some value. Notice how both sides match. Don't they approach the same value from here and from here? We're both actually getting close to 0. It's both 0, 0. It's an origin there. So that's why I put 0 here. Again, doesn't matter if there's a hole there. We're approaching it. Again, you're going to see this numerically very soon. We're getting close to this value, and it's 0. So both sides match, so we have a limit. And what is the limit? It's that the y value that would have been there, even if there was no hole. Now, what about x approaches 2? Now, that's a different story. Notice how there is a break. So from the left, looks like we're approaching some negative value. We don't know what it is, but it doesn't matter. Now from the right, we're getting closer to the hole, but again, it's going to be some positive value. So here's negative, here's positive. There's obviously a break. They do not match. So the limit does not exist. So always go back to that definition of both sides matching. So make sure you check both of them on the graph. So now how do we compute a limit? There's 3 ways we can do this. You can use a graph if you have a graph like this. You can use a table of values. We're actually going to use graphing calculator here. So get your graphing calculator ready for this rest of the video so you can follow along. Or algebraically, sometimes you can do this. There have to be certain conditions that apply here, like if you can factor, but we can do it sometimes. So let's take a look at the table first. That's the quickest way to do it if you have an equation and you don't have the graph. And we're going to talk about algebraically also, but let's talk about table of values right now. So let's say we have a function, 2x squared minus 4x plus 7. And we're trying to figure out limit as x approaches 1. Let's use a table of values. Now, the first time you're going to do this, when you get your graphing calculator, you want to make sure set it up. Here's my graphing calculator. Go to second window. Notice how you have a bunch of things here, but notice how both independent and dependent value are set on auto to begin with. It's so your calculator can compute it automatically. But if you put an independent value on ask and click on enter, leave the dependent on auto so the calculator can compute them. And now you can input any independent values or x values basically for your function. And that's kind of nice. You can actually do this on the table. Otherwise, you have to do it by hand and it takes a while. Once you do this, you don't have to do it again. So then go into y equals to, and what was our function real quick? Let me take a look. 2x squared minus 4x plus 7. So 2x squared minus 4x plus 7. Okay? Now, you don't even have to graph it unless you want to see what it looks like. But go into second graph. Here's our table. Even if you have something here already, do not worry because you can type over it and you'll see it shortly. Now, we were trying to do limit as x approaches 1, I believe. So how do you do this? Let's take a look real quick. Let me try to scroll down. All right. So notice how I have this table here. You want to basically approach it from both the left with values smaller than 1, but kind of getting very close to it. And same thing on the right. Excuse me. Sorry. But notice how we start with 1 decimal, then we progressively, the values are actually getting smaller, but we're progressively getting closer to 1. So you'll start seeing patterns very quickly, I think. So let's actually manually input them. So 0.9. Now let's do it with 2 decimals. So let's do better than that. 0.99, 0.999. So you want to see a pattern with the y values. Does the left side, does the y values approach a certain value? So here it looks like it's 5. Pretty obvious, but sometimes it takes a little while. So it's up to you how many you're actually going to use, unless it's kind of given in the problem already. How about the other side? Let's start with, again, 1 decimal. Let's start with 1.1. Now, notice how the next one would be 1.01. Because you want to get closer to 1, not 1.1 itself. So you don't want to put like 1.11. That's not getting closer to 1. You want to go in the opposite direction. But notice how we're still, let's do 001. Okay. So notice, yeah, sure, you can put in the actual 1, and here you'll get 5, and they happen to be the same, but you're not always going to get this. So you'll see it very soon. So notice how both sides approach 5. So what is our limit? It's 5, because both sides match. Again, you want to see a pattern, and you want them both approaching the same value. Kind of like from here and then from here. Okay? Let's try it with this one. Okay? It's a little bit more complicated. So what you want to do, go to y equals to, clear out your previous function. You want to put parentheses, unless you know how to do fractions on your calculator, which then you can do it. Then you do second radical, x, make sure get out of the radical, minus 3. Okay, so make sure definitely that not the whole thing is under the radical, otherwise you'll get something else, divided by, again, you want your denominator, what was it, x minus 3, I think, yep, x minus 3. Make sure your both numerator and denominator are in parentheses. I made that mistake earlier, had to re-record this video. Anyway, second graph, notice how we go straight to the table. Notice how previous values are there, type over them. What was the limit? I think we wanted to approach limit as x approaches 3. Okay, so how do we do this? Let's do it, actually, if you go up to here, right now, notice how the values that I have, maybe pause this video, think about it, and try to input this. And when you get back, we'll compare it. Okay, so hopefully you had a chance to try it out, but what do you do? So how do you get close to 3? So let's start with 2.9. This is from the left. Then how about do better than that? 2.99. See the pattern? Then do better, 2.999. Okay. Something funny is happening to the values. They're actually keep on growing, but okay, let's try the other side. So we're a little bit bigger than 3 now, 3.1. Okay. Let's do better but closer to 3. So 3.01 and 3.001. Something is happening. We're not getting okay, so let's try actual 3. What's going on there? Error. Something is happening. So what's going on here? Well, first of all, you are dividing by 0. This is what I was talking about, being a hole there, or maybe an asymptote, which this is the case of an asymptote actually. So like maybe in this graph, the one side, and actually if you graph it, you'll probably see it. One side is approaching infinity. It's definitely an asymptote here. But the other side is approaching negative infinity. So what's happening? If you see, again, on this side, they're getting really large but positive. On the other side, they're getting really large but negative. Both sides do not match. So the limit does not exist. Now, what if we ask the same question, but if this was a graph and let's say they were both approaching the same infinity, okay, maybe positive infinity. So if you can kind of tell, both sides are going up, okay? So the limit, if I can write it, limit as x approaches certain value, it's always attached to a function, would be positive infinity. So in this case, we'll put infinity or with a plus, same thing. So yes, if they go to the same infinity, your answer could be infinity. It depends on the book. Be careful if you're taking like Calc 1 or something, if you're taking another Calc course. But from this course, if both sides match, if they go to the same infinity, the answer would be that infinity. Again, it's going back to the definition. But in this case, they're going in opposite directions, so it does not exist. Now notice, again, the limit did not exist, but yeah, we couldn't even get the y value either. So the limit happened not. So here I explained the same situation. So if it was approaching same infinity, same thing with a negative, okay, that would be the limit. All right. So here we're gonna approach. So here's this is what I'm explaining right here with the infinities. Okay. Now, this is one way to do this, and if you had something like limit as x approaches 0 of f of x. I don't know if there are any examples of that, but maybe it's good. How do you make your table? So again, sometimes on the homework the table is given, but I do want you guys, first of all, practice writing this limit notation, and hopefully your writing looks a little better. It's kind of hard to write on a tablet. And so practice this, and also practice making your own table. I think that pays. So how do you do it if x approaches 0, for example? I would do it like this: negative 0.1, negative 0.01, and then negative 0.001. Okay? Same thing from the right. I would do it with a positive 0.1, if I can write it. Then 0.01, and so on. So you'll see the idea. So you're actually approaching 0 from both sides. Okay? The left and the right. And again, you want to compare. And a lot of times on the homework, the table looks like this, so you can see how they kind of converge. You see how I have the two arrows here? So what's happening in the middle? So you're approaching it from the left, you're approaching it from the right. It's a little bit more visual how it is on the number line. And again, both sides are wildly different, so the limit does not exist. But if they were both approaching the same y value, then the limit would be whatever it is. 5, 3, whatever the number happens to be. Could be negative, and so on. Now, here is a neat little trick or definition, if you think about it. And we'll discuss this in the next section quite a bit. But what does this mean? But if the function is continuous, then the limit is actually the y value. Because there is no hole, there is no asymptote, there is no problem, so they both would be actually exactly the same. So we're going to use this. Now, because in the section we're kind of doing it both ways, we're actually going to try to do it algebraically as well. So basically, always your first instinct would be, if you're doing this algebraically, plug in the value. Like, let's say, here's an example. Limit as x approaches 3 of x squared minus 9 over x minus 3. Your first instinct, plug in the 3 and see what happens. Now, unfortunately, we get 0 divided by 0, which is undefined. Well, for us, it's actually going to mean something. Means there is a hole, and there is actually a limit. So here is the situation where you do have a value for the limit, but you do not have the actual y value because it does not exist at the hole. So here is where it would not, this situation would not happen. They're not going to be equal right now. But there is something we can do. Okay, what can we do? You can use a table, just like we did in the previous. You could have done the 2.9, 2.99, and from the other side 3.1, 3.01, and compare. Or, if it is a hole, if it is 0 over 0, then what can we do? Here is this definition. If it's continuous, we can just plug it in. Here's an example, okay, before we get back to the previous example. 2x plus 1. Any polynomial is a continuous function. Why? Because there's no denominator, you're never going to divide by 0, there are no radicals, there are no problems. Simply plug it in. Notice how I don't even write a limit anymore. As soon as you plug it in, voila, here's your answer. Sometimes it's a very quick way of doing this if you want to compare. See, you didn't make a mistake with the the definition. So you get 3. And if you have 0 over 0, like the situation with a hole, the function is not continuous, but it does not mean we cannot do this. Yes, we can. Okay, think of a slogan if you want. What can you do? A hole is sometimes called removable discontinuity. If you look it up on Google, you'll see it right away. It's also called, how do we remove it? Sometimes we can factor like this. Notice how x squared minus 9 was a difference of squares, x minus 3 times x plus 3. Get rid of the problematic factor in denominator that gives us a 0. We're left with just x plus 3, and we can plug in the value, which happens to be 3 also. So we'll get 3 plus 3, and it's 6. So in this case, the answer is 6, even though if you actually graph it, unfortunately, when you graph it in a graphing calculator, it's not going to show you the whole, but the function does look something like this, you know, if this is 6 or something like that. So be careful. You may not see the whole in the graphing calculator. The only way you'll see it is like if you do the table, and it's going to show you the error, just like we tried it, I think. And even Desmos does not show you that. And by the way, if you haven't checked out Desmos yet, definitely do it. That was on Blockboard, so check that out. So if you try the table calculator, you should get the same answer. Sometimes if you have a complicated question like with exponential function, maybe not in this book, but it can happen, you still have to use a table or calculator, numerical way. So sometimes the algebraic way is not possible. But if it is possible, hey, that's another way to do it. Okay? Now, occasionally you'll have a number over 0, like let's say 2 divided by 0. In this case, you'll get an asymptote, okay? And if it is an asymptote, you want to graph the function and you want to see, do both sides go to opposite directions? Remember how we did that example? Or you can do it with a table. If they do, the limit does not exist. If they go to the same direction, positive infinity or negative infinity, the limit's going to be infinite. So the limit does not exist, or in case of an asymptote, and I'll say that again in a separate video, or infinite. So if you ever get something that's not 0 over 0, then that's what happens. But in a lot of these examples, like number 2 right here, you will get 0 over 0. So here, try this again with negative 2. You'll get 0 in denominator, definitely. You should get 0 in the numerator as well. Okay? Same idea happens. You can factor and you can get rid of it. So definitely it's 0 over 0 or a whole. Right here. Okay? Whole situation. But we can still do this. We can get rid of that factor and we can plug it, and voila, here is the result. Okay. Now the last aspect in this section, and there is a lot going on, so definitely spend some time with the homework. But the last thing is limits at infinity. I'm going to do it in the next video, so this one is not too long. And we'll talk about that one. Okay, see you in the next one.